Hello, everyone, and thanks for giving me this chance to present part of our work in IPSL. I am Kazem Ardaneh, computer scientist at IPSL, and I would talk about IPSL climate models on the heterogeneous architecture. So at the moment, the IPSL climate models that in the left of the screen, we have the atmosphere model plus the land model, which are coupled together, and then we have a ocean to model the oceanic and also the XIOS for handling the input-output data. At the moment, the current parallelism in the model is in the atmosphere and space model is MPI for when we decompose the domain between the processor, and in each processor, we use the OpenMP. But the NEMO model is full MPI. So we target for the next architectures, which we use the MPI plus OpenACC, that we can use both domain decomposition based on the MPI, transform the calculation on each CPU core to GPU to also benefit from the GPU calculation. So the things which we follow is as in the right side, in the right side of the screen. So we decompose the domain between the CPU processor, and we launch using the OpenACC one GPU card for each processor. So if I give you a very brief difference between the CPU and GPU, there was a very good talk, I think, yesterday about this. So in principle, so the CPU is more fast for when we do the job in the serial, and GPU is good for parallelism when we have lots of work to do at the same time. So in fact, is the difference between the throughput and speed. So, and which of them is useful for us? That's highly depend on the on the calculation that we need to do. So, in fact, in the heterogeneous model for EPSL, we wanted to use both of them because part of the calculation need to stay on the CPU, but the most consuming part we port it on the GPU. To do this heterogeneous parallelism, so there are a few ways to do it. The first thing is to use, for example, the available libraries that are optimized for the accelerator, like FFT or linear system solver. Another one, which is more portable and more simple to implement, but it has limitation in terms of what we can implement in the code, is using the compiler directive, for example, like OpenMP or OpenACC. But there is another method that is more flexible to change the parallelism, but also that's more portable, is using, for example, the MPI or CUDA for doing the process CPU and GPU parallelization. What we use here is based on the CUDA programmation paradigm, which is based on the dividing the grid of work, dividing the work in the grids, and in each grid we have block of work, and each block of work is divided to thread of work. So in principle, if we have, for example, this photo, after using the CUDA, we would have something like this, that we separated between different block of work, and each block of work we ported for different number of threads to all of these jobs can be done in the same time. So that's what means the throughput. So all of these jobs are done at once. So for our work for IPSL model, we use as I say, we use MPI for domain decomposition. In the next stage, we use OpenACC for it. We use NVIDIA SDK programming kit. That it has almost all the tools that we need, for example, compiler libraries and profiler and debugger. We try to use one model of porting, very simple and simple to follow, and also can be modified by everyone. So we, in principle, we port the most consuming part of the code in the GPU. So, and for that, we put the calculation in the kernel of in the structure of kernel. That kernel is part of calculation, which would be executed on the GPU. For this, I show part of the speed up that we have in terms of just to show you always GPU cannot be a good choice. Sometimes we need to use CPU. So here is the runtime that we have on the CPU. So for example, the most consuming part until now for us is these routines. And if we go, for example, to the left, we see the lower consuming routines. So, but if we port this routine on the GPU, we see that for the low consuming routines, the speed up is not very good. But as we go to the higher consuming routines, we have a good speed up on the GPU. So that was what I wanted to present for you. So in summary, I can say that OpenACC offer a useful and simple paradigm for a GPU calculation, and is simple to implement. It's powerful. I would say that the speed of the OpenACC in comparison with the CUDA is almost half, so it's not very bad. So, and it's for the community code like IPSL, the things that is most important for us is the portability of the code. So, and it's very portable using OpenACC, but there is a downside of the OpenACC that's by now is just limited for the architecture that are supported by NVIDIA. So that was all for me. So thank you for your attention, and let me know if you have a question.